Alright, so earlier I described that we want to get our change in enthalpy to be equal to 0 for this problem. So that means we need to figure out how to calculate our enthalpy. So a way to calculate enthalpy is, a small change in enthalpy is equal to partial derivative of enthalpy with respect to temperature, holding pressure constant with a small change in temperature. And this is for an ideal gas. If we had a non-ideal gas, we'd have to have another term related to the pressure, but this is an ideal gas, so we don't need that other term, and this is the equation that we can use. So then we can simplify this a little bit. So this term right here is the heat capacity. So we can write that our change in enthalpy is equal to the heat capacity with the change in temperature. And then we can go ahead and integrate those, and we'll have this from temperature 1 to temperature 2. So for our problem, temperature 1 is going to be 298 Kelvin, and then temperature 2 will be the temperature of our flame, which is what we're looking for. And then enthalpies will be integrated from enthalpy 1, so that's the enthalpy of reactants going in, to the enthalpy 2, which is enthalpy of the products that come out of the flame. And then this whole term right there is just the change in enthalpy. And we can rewrite this side. So this is kind of how we're going to, calculate this problem. So we're going to be using a library that uses ChemCAD. And I forgot to write, so that this is which equation this is. So we're going to use a library that has data from ChemCAD, which is a program, and it uses a bunch of different equations. And the equation that is most relevant to us is equation 107, which I have written out for us right here. And this is the equation it uses to calculate the heat capacity. It has some coefficients and terms, the A, B, C, D, and E, and we can pull those parameters from this library that we're going to use. So we can use this expression for heat capacity inside this integral here. So we can say, that delta H, the change in enthalpy, is going to be equal to, and then actually I'm going to kind of split this up, so I don't write this all inside one integral. I'll kind of split up the integrals by terms, so like one there, one there, and one there, and I'm going to write it like that up here. So I'm just, copying this down up here inside the integral. All right, dt up there. Okay, so move over here so you can see it. So this is the integral that we're going to want to solve, and we can do some of these by hand, but as soon as we get to the hyperbolic sign and stuff, I don't want to do that by hand. So we're going to use Wolfram Alpha to help us. So we do this like this first term by hand. So that will be delta H is equal to, so derivative of A with respect to time is just going to be A time, or not time, temperature. With respect to temperature, it's going to be A times that temperature, and then this whole thing that we get is going to be evaluated from T1 to T2. Alright. And then we'll have B, that's a constant, times what we get for this. So let's type that into Wolfram Alpha to see what we get. Alright, so I've put up Wolfram Alpha for us here, and we're going to just take this term by term and plug it in. So we're going to integrate, and then we're going to integrate, so it's C divided by T parentheses around that, divided by the sine, hyperbolic sine of C divided by T. Actually going to want a set of parentheses around there, and then that's squared, and we want to do it with respect to temperature. So let's do that and see what it gives us. So that's a pretty simple integral, so we can write that down up here. So the integral of that is going to be C times the hyperbolic cotangent of C over T. Alright, and then for our final term, we're going to have D, because that's a constant here, and then times the integral of this. So I'm going to type that one in as well. And I'm actually going to change this one slightly because it's very similar. So instead of C's, we have E's. And instead of a hyperbolic sine, we've got a hyperbolic cosine. Alright, and we're going to enter that in. Alright, and then we got, we need to be careful with the negative here. And then we've got that the derivative of this, or the integral of this is negative E times the hyperbolic tangent of E over T. And so that is going to be our expression for delta H. And so yeah, so we'll evaluate it at T1 and subtract it by the evaluation at T2 to get our delta H, set that equal to 0, and we should get our temperature of our flame. Alright, so the next thing we're going to want to do is we're going to want to work on putting this integral that we derived earlier into our code. So so that we can calculate the enthalpy and then set it to 0 eventually. So what we're going to do is we're going to define a function that will return our integral. So define integral, integral of the heat capacity. So we'll put it like that. And we're going to input our temperature, because that's what is our independent variable here. So then we're just going to return the integral that we calculated. So it'll be A times T plus oh, right, so for A, alright, so we haven't defined A yet. I'm going to write them out like this. So A is going to be equal to, so we're going to get these from the library that we imported earlier from GitHub that we put for all of these. So A is going to be equal to cp.cp ig and then A. So what this means is this, I mean, this is just a function to call that value, but it's, you know, it's heat capacity for an ideal gas, and then it's parameter A. So that's going to be that. B is going to be equal to that, but B, I'll actually copy this whole thing. And need C. Nope. I know. D and E. Okay, so then C and C, and then this is D. That is D. And then that's E. That's E. That way I don't have to type it all, you know, in a bunch of times. So now we've got A times T, and then we've got plus B times C times NP dot cotangent hyperbolic of C divided by the temperature. Alright, and then close those parentheses, close parentheses, and then plus D times, oh, we need a multiplication sign over here as well. There we go. And then negative E times NP hyperbolic tangent of E divided by T. Alright, shifting on that. Alright, appears to have worked. And then we're going to want to, you know, evaluate it from temperature initial to temperature final. So we'll define another function that will do that. So define, and this will give us our final enthalpy. So input the temperature, and then we're going to call, we're going to return. So we're going to have integral CP of, so final minus initial, so the final will be the temperature that gets input, and then initial will be 298 because that's standard state, and then, alright, I forgot a step up here, so it might not be an obvious step, but if we go into the files and just choose a random compound here, make that smaller, we can scroll down to where, so like this is all of the data that it's pulling from, and if we get down to where, I think I went too far, okay, so ideal gas heat capacity, so that's what we're pulling from. This is in kilomoles, and we have this up here is all just in moles, so we're going to want to divide our final thing by 1,000, just to make sure that the units match. Did I put that? I don't know where the other parenthesis went. I'll add it again. Alright, close that. Make this back about even. Alright. So shift and around there. Alright, so then, alright, back to this. So now we have what is going to be, you know, the difference of this integral. And then we're going to need to add this to the heats of formation of each of these components to get like the overall, because this is just the change, it's not like the actual enthalpy, it's just the change in enthalpy from where each component started, and they started at their heat of formation of their ideal gas. So we're just going to add, and we can get that from P dot, and we can get, it's the heat of formation of the ideal gas. So just like that. So we can shift on around there. And now we have our function that will calculate our input. Alright, so the next thing we're going to want to do is we can compare our results to the library that we have from ChemCAD and make sure we're getting, you know, reasonable values. So to do that, we're going to, we can first call in from ChemCAD where the enthalpy values, so that is enthalpy of the ideal gas, so like that, and then we input 1 mole because we have 1 mole of gas, and then we can choose a temperature, so maybe 300 Kelvin. So shifting around that, and that is the enthalpies that ChemCAD has for a temperature of 300 Kelvin, and then for each of these components, and then we can do the same with our function, so enthalpy of 300, and then we got an error. This module numpy has no attribute cotangent of h. Oh, so okay, so it must mean that we can't do cotangent. The hyperbolic cotangent's not a thing, so we're gonna have to do 1 over the tangent hyperbolic. So that should be an easy fix. So do we just need to put this 1 divided by that, like that, and then I think it should work out all right. All right, so you can see we're getting pretty similar values, not exactly the same, which is fine, but they're reasonable. You know, you can see that for methane, it's, you know, negative 7.47 times 10 to the 4th, and we've got negative 7.47 times 10 to the 4th as well. So like to a couple significant figures, you can see that these values are quite similar, though not exactly the same. But that's just a good check to make sure you're getting semi-reasonable values for your code.